Perturbation theory comprises mathematical methods for finding an approximate solution to a problem, by starting from the exact solution of a related, simpler problem. A critical feature of the technique is a middle step that breaks the problem into solvable and perturbation parts. Perturbation theory is applicable if the problem at hand cannot be solved exactly, but can be formulated by adding the small term to the mathematical description of the exactly solvable problem. Perturbation theory leads to an expression for the desired solution in terms of a formal power series in some small parameter, known as a perturbation series, that quantifies the deviation from the exactly solvable problem. The leading term in this power series is the solution of the exactly solvable problem, while further terms describe the deviation in the solution due to the deviation from the initial problem. Formally, we have for the approximation to the full solution a series in the small parameter, like the following. In this example, A0 would be the known solution to the exactly solvable initial problem, and A1, A2 represent the higher-order terms which may be found iteratively by some systematic procedure. For small epsilon, these higher-order terms in the series become successively smaller. An approximate perturbation solution is obtained by truncating the series, usually by keeping only the first two terms, the initial solution and the first-order perturbation correction. General description. Perturbation theory is closely related to methods used in numerical analysis. The earliest use of what would now be called perturbation theory was to deal with the otherwise unsolvable mathematical problems of celestial mechanics. For example, the orbit of the Moon, which moves noticeably differently from a simple Keplerian ellipse because of the competing gravitation of the Earth and the Sun. Perturbation methods start with a simplified form of the original problem, which is simple enough to be solved exactly. In celestial mechanics, this is usually a Keplerian ellipse. Under non-relativistic gravity, an ellipse is exactly correct when there are only two gravitating bodies, but not quite correct when there are three or more objects, and not quite correct when the gravitational interaction is stated using formulas from general relativity. The solved, but simplified problem is then perturbed to make the conditions that the perturbed solution actually satisfies closer to the real problem, such as including the gravitational attraction of a third body. The conditions are a formula that represent reality, often something arising from a physical law like Newton's second law, the force acceleration equation. In the case of the example, the force F is calculated based on the number of gravitationally relevant bodies. The acceleration A is obtained using calculus from the path of the Moon in its orbit. Both of these come in two forms: approximate values for force and acceleration, which result from simplifications, and hypothetical exact values for force and acceleration, which would require the complete answer to calculate. The slight changes that result from accommodating the perturbation, which themselves may have been simplified yet again, are used as corrections to the approximate solution. Because of simplifications introduced along every step of the way, the corrections are never perfect, and the conditions met by the corrected solution do not perfectly match the equation demanded by reality. However, even only one cycle of corrections often provides an excellent approximate answer to what the real solution should be. There is no requirement to stop at only one cycle of corrections. A partially corrected solution can be reused as the new starting point for yet another cycle of perturbations and corrections. In principle, cycles of finding increasingly better corrections could go on indefinitely. In practice, one typically stops at one or two cycles of corrections. The usual difficulty with the method is that the corrections progressively make the new solutions very much more complicated, so each cycle is much more difficult to manage than the previous cycle of corrections. Isaac Newton is reported to have said, regarding the problem of the Moon's orbit, that it causeth my head to ache. This general procedure is a widely used mathematical tool in advanced sciences and engineering. Start with a simplified problem and gradually add corrections that make the formula that the corrected problem matches closer and closer to the formula that represents reality. It is the natural extension to mathematical functions of the guess, check, and fix method used by older civilizations to compute certain numbers, such as square roots. Examples for the mathematical description are an algebraic equation, a differential equation, a free energy, a Hamiltonian operator. Examples for the kind of solution to be found perturbatively: the solution of the equation, the statistical average of some physical quantity, the ground state energy of a quantum mechanical problem. Examples for the exactly solvable problems to start with: linear equations, including linear equations of motion, statistical or quantum mechanical systems of non-interacting particles. Examples of perturbations, to deal with nonlinear contributions to the equations of motion, interactions between particles, terms of higher powers in the Hamiltonian, free energy. For physical problems involving interactions between particles, the terms of the perturbation series may be displayed using Feynman diagrams. History: perturbation theory was first devised to solve otherwise intractable problems in the calculation of the motions of planets in the solar system. The gradually increasing accuracy of astronomical observations led to incremental demands in the accuracy of solutions to Newton's gravitational equations, which led several notable 18th and 19th century mathematicians to extend and generalize the methods of perturbation theory. These well-developed perturbation methods were adopted and adapted to solve new problems arising during the development of quantum mechanics in 20th century atomic and subatomic physics. Beginnings in the study of planetary motion. Since the planets are very remote from each other, and since their mass is small as compared to the mass of the Sun, the gravitational forces between the planets can be neglected, and the planetary motion is considered, to a first approximation, as taking place along Kepler's orbits, which are defined by the equations of the two-body problem, the two bodies being the planet and the Sun. Since astronomic data came to be known with much greater accuracy, it became necessary to consider how the motion of a planet around the Sun is affected by other planets. This was the origin of the three-body problem. Thus, in studying the system Moon-Earth-Sun, the mass ratio between the Moon and the Earth was chosen as the small parameter. Lagrange and Laplace were the first to advance the view that the constants which describe the motion of a planet around the Sun are perturbed, as it were, by the motion of other planets and vary as a function of time, hence the name perturbation theory. Perturbation theory was investigated by the classical scholars Laplace, Poisson, Gauss, as a result of which the computations could be performed with a very high accuracy. The discovery of the planet Neptune in 1848 by Urbain Le Verrier, based on the deviations in motion of the planet Uranus, represented a triumph of perturbation theory. Rise of understanding of chaotic systems. The development of basic perturbation theory for differential equations was fairly complete by the middle of the 19th century. It was at that time that Charles-Eugene Delaunay was studying the perturbative expansion for the Earth-Moon-Sun system, and discovered the so-called problem of small denominators. Here, the denominator appearing in the nth term of the perturbative expansion could become arbitrarily small, causing the nth correction to be as large or larger than the first-order correction. At the turn of the 20th century, this problem led Henri Poincaré to make one of the first deductions of the existence of chaos, and what is poetically called the butterfly effect, that even a very small perturbation can ultimately have a very large effect on non-dissipative or friction-free dynamic systems. A partial resolution of the small divisor problem was given by the statement of the Kam theorem in 1954, developed by Andrei Kolmogorov, Vladimir Arnold and Jürgen Moser. This theorem stated the conditions under which a system of partial differential equations will have only mildly chaotic behavior under small perturbations. Application to new problems in 20th century physics. Perturbation theory saw a particularly dramatic expansion and evolution with the arrival of quantum mechanics. Although perturbation theory was used in the semi-classical theory of the Bohr atom, the calculations were monstrously complicated, and subject to somewhat ambiguous interpretation. The discovery of Heisenberg's matrix mechanics allowed a vast simplification of the application of perturbation theory. Notable examples are the Stark effect and the Zeeman effect, which have a simple enough theory to be included in standard undergraduate textbooks in quantum mechanics. Other early applications include the fine structure and the hyperfine structure in the hydrogen atom. In modern times, perturbation theory underlies much of quantum chemistry and quantum field theory. In chemistry, perturbation theory was used to obtain the first solutions for the helium atom. In the middle of the 20th century, Richard Feynman realized that the perturbative expansion could be given a dramatic and beautiful graphical representation in terms of what are now called Feynman diagrams. Although originally applied only in quantum field theory, such diagrams now find increasing use in any area where perturbative expansions are studied. Search for better methods for quantum mechanics. In the late 20th century, broad dissatisfaction with perturbation theory in the quantum physics community, including not only the difficulty of going beyond second order in the expansion, but also questions about whether the perturbative expansion is even convergent, has led to a strong interest in the area of non-perturbative analysis, that is, the study of exactly solvable models. Much of the theoretical work in non-perturbative analysis goes under the name of quantum groups and non-commutative geometry. The prototypical model is the Korteweg-de Vries equation, a highly nonlinear equation for which the interesting solutions, the solitons, cannot be reached by perturbation theory, even if the perturbations were carried out to infinite order.